So, today we will continue with the event control. I think yesterday we were looking at. So, the indirect design means by provision of additional system implementation, basically like for example, typically ductility of the material to make the structure fail by ductile instead of say brittle failure. So, that is the idea behind, though it is not a direct design, you have not actually provided additional strength or additional measures, but by selecting suitable material we have made the structure to be failing by ductile nature. The other method is providing redundancy. For example, you take a portal frame and if one of the column fails, the system fails. So, instead if you provided X brace with the portal frame, probably you have a additional bracing, which may, even if one of the brace fails, the other brace will take over and provide stability for certain amount of loading. So, that is exactly the indirect design means provision of system where those facilities will cause the structure to fail either slightly later, that means additional load can be taken, or fail by ductile nature, that means immediately it will not collapse. That is the idea behind the indirect design. These are some of the provisions. Actually, if you read many of the codes, whether it is IS code for concrete design, steel design or other codes, you have several provisions by means of this kind of ideas, making the structure to have ductile behavior during taking the load as well as to the ultimate capacity. Provide connections of primary members, which I think I emphasized during our design of tubular connections. Always have the joint design having extra strength or extra margin compared to members. You can have one member fail, the system does not collapse, but if one joint fails, you look at the joint that we have had a look at for jacket structures, one joint carries 7-8 members. If one of the joint goes, almost the system becomes unstable. So, that is why provide connections of primary members with a strength exceeding that of parent member wherever the members are. Provide redundancy in the structure, which typical example will be our X brace, 2 legs with an X brace of this kind. If one of the brace fails, the other brace will take the load by redistribution. So, that is exactly the idea, that though it is not a direct design method, but these are some of the recommendations you will read. Actually, if you go through API, these are the recommendations given in there indirectly. So, when you satisfy this, automatically the structure has the sufficient strength for ductile nature of failure. Avoid dependence on energy absorption in struts with a sharply decreasing post buckling capacity. Basically, for example, you have one member which later on we will design it, which is going to be designed for a energy absorption for say ship impact, but the support members are so small, if one of that member fails, for example, the whole system fails. So, do not depend on such kind of design. What you need to have is additional members to support that same energy absorption capacity. Select material with sufficient fracture toughness. This is what we were looking at in fact during our fatigue design. Fatigue is directly proportional to the toughness of the material or the characteristic of material against fracture, which gives you an idea that there is no direct relation to strength. So, toughness makes so much importance, because initiation of crack depends on the material, the crystal structure to open and propagate. So, basically that you normally select sufficient toughness, especially for materials serving low temperature service. For example, in substructures always going to be temperature less than 20 degrees, some areas can be less than 0 degrees, like if you go to North Sea. Select material such that the ultimate tensile strength is higher than the yield strength. For sure, you might have learned your the tensile test, always yield strength and then you have the ultimate tensile strength. So, now if you see the difference between the yield strength and the tensile strength larger, is a good material, is not it, because even after yielding you have a larger redistribution to happen, whereas if you have yield strength and just a horizontal curve, for example, a typical elastic perfectly plastic material. So, this is your strain, this is your stress. You might have seen the stress strain curve for typical steel material. If you have something like this, elastic but perfectly plastic, not very good. If you have something, you will see most of the steel, that is your ultimate failure point, isn't it? If you see something like this, the larger the difference between the ultimate point or the so called tensile strength, breaking load strength to a yield strength, that means even after yielding you see a particular location in the connection or in the member yielding starts, but still does not fail, because you still have the sufficient strength before it breaks away, and that is where. So, you need to see that ultimate strength is larger value. Design of joints and members through inelastic deformation to meet the compact section requirement, that means it should fail by basically the yielding rather than buckling. So, indirect design means you have provisions in the design procedure which automatically satisfy. Most of them are actually, if you read the codes, you really do not have to make any effort in designing. These are the guidelines you must follow. Most of the codes are mandatory. Direct design is very simple. This is where we are going to spend some time. Basically, look at the fire as the design load or a scenario that creates additional load to the structure, and then evaluate the strength. Go back to the original design principle of demand versus capacity. In this particular case, what is going to happen is, when the fire occurs in a particular location in a structure, the structure gets heated up, and the structure is part of a bigger frame where it is trying to expand, because you know very well the steel thermal expansion coefficient. So, it is going to expand. As long as you allow the expansion to happen, there may not be much problem actually, but the main issue here is it is connected to another part of the structure. You may not actually permit expansion. When the expansion is restricted, what will happen? The induced stresses and forces will be so enormous that the supported members will fail. That is the idea behind. So, it is trying to expand, and the supported members will deform excessively, either by bending or by shear or whichever the weakest means. So, that is where this direct design approach is to evaluate the resistance of the members against the thermal induced forces, and that means we need to find out what is the temperature and what is the duration, because steel is not going to just 1 minute you have a 1000 degrees and then just come down to 0, it is not going to expand so fast. So, basically we need to see how long the persistence of the fire is happening. So, this characteristics of the fire is as important as the characteristics of material. So, that you can actually superimpose both of them and find out how the behavior, we are going to see that. Of course, absolute means of direct design is also not so good, because you may actually spend a lot of money on that. So, we need to find out how much direct design you would like to make and how much indirect means of enhancing the structural capability against fire, then you just provide. So, design for fire as a loading condition needs to be evaluated quickly. So, just we will look at the sources of fire. Hydrocarbon direct fire, which is basically ignition by means of direct onto the hydrocarbon, or you could have blast initiated, collision initiated, or drop object initiated. All of them are making spark and you have the fuel to burn. So, main idea is the fire to continue and to persist for a longer duration of time, you need supply of fuel for sure, without which you will be, the temperature will come down, and also the supply of oxygen, very important, otherwise you will not be able to burn any fuel. So, basically fuel and oxygen is very essential requirements for a fire to persist for a longer duration. And of course, sources of ignition, you could have purposeful ignition, which is normally not there in the such kind of facilities, sabotaging, whereas you have indirect means of ignition like blast or kind of collision or electrical faults can cause basically ignition there. Dropped object, most of these three things are actually just rubbing surfaces. In fact, if you look at one of the fire happened in 2005, I did not know, I do not know whether I have mentioned to you earlier on, this fire caused by a simple boat collision with the structure, which caused a rubbing surface, and thus surfaces created spark, and that spark together with the damage on a riser line, just the gas got into fire and blast. So, basically you can see there is no ignition by somebody, there is no machine which is actually having fire, just a cold gas, but just a rubbing surfaces, impact, gas come out, and that spark created the fire and then explosion. So, you could see that the ignition is not a very difficult thing to happen, as long as you have huge amount of fuel and the oxygen presence, fire is imminent. As long as any of such things like these three things happen, you will be having fire. So, that means the facilities having large inventory of hydrocarbon fuel is potentially high probability of fire occurrence, unless all the safety precautions are strictly followed. Now, you could see that is why we need to see the platforms should be divided into or segregated into zones of different safety. It is not that basically unsafe or safe zone. In notation basis we can call it all are safe zones, only thing is in terms of presence of higher the hydrocarbon, because the potential of fire is more. So, we should not actually call it safe zone, unsafe zone, basically process zone, living zone and utility zone, basically different amounts of safety levels. Of course, during the normal working condition all areas are safe, only thing is the practice will be different. When you reach a process zone, you need to have sufficient safety equipments, whereas in the living zone, for example, you live inside a living facility, you do not need any of the safety kits with you. For example, if you go into a process area, some of the platforms handle sulfur, when you enter into that area you need a mask, otherwise the colorless gas can kill you instantaneously. So, basically you need to go there, you need to have your safety kits. If you go into open area, you need a helmet. So, the idea is to identify these zones to make sure that whenever you go there, you need to have such equipments with you. Living zone always will be made very safe, because you are going to live there, you can't live with all the time the safety equipments, which is why you make the barrier so safe that if you are inside, you do not need to have much worry. Of course, you still need to follow certain the principles when you are in offshore. Utility zone is basically have equipments very similar to onshore facilities. You may have a power plant, you may have a water treatment plant, all of them are safe zones. Only thing is still you have potential of propagation of fire from process zone to the utility zone, because you still have fuel for these machines. For example, if you have a power generator, power cannot be generated without a fuel. So, you have a limited amount of hydrocarbon, and which can also cause potential fire. So, you look at these two typical platforms, basically just to give you an idea that there is no absolute term called the right or the wrong layouts. I think this goes to not only to offshore platform, for any facility there will always be multiple arrangements, which could be either called safe or unsafe. Now, if you look at this left side one, you can see here on the leftmost side you have the living facility, which is basically somewhere here, accommodation facility, and then followed by several equipments and facilities for production, utilities, whatever we see there. On the right hand side you see a drilling rig, something like this, drilling mast, and below which you see the, I think most of you are able to understand what is this conductors, basically is the drill casing. So, you see here on the right side you have the drill facility, associated well platform connected to production cum living facility, all of them are together. But one thing what they have done, they have segregated in a nicer manner. The extreme right side you have the well facility, extreme left side you have the living facility. So, they are kept apart, so that in case of an accident or in case of a fire, the drilling or the well facility will not cause much problem to the living facility. So, the idea is little bit of thinking has been done, instead of putting the living facility at the middle, which will be very safe because at the central column, but in terms of safety levels of fire and safety is not very good, because it is too close to the well facility. Whereas, if you come to the next option, you see here the well facility is at the middle, and there are some other facility like flaring towers on the right side and living facility on the left side. Together at the bottom you have several production facility. You can see here sometimes people have done the left side or the option 1, so let us call it this option 2. So, you do not see here some logic is missing. Why the well has been placed at the center, why the well has been placed at the right, all depends on the configuration of the substructure and the arrangement, but both of them can be made safe. You can't call them one of them is safe, one of them is unsafe. In this particular one, what you see here, the black color or the barriers are kept in place in such a way that propagation. So, the inherent safety is not achieved, but the safety is achieved by means of additional safety features you incorporate in the system layout. So, that is the idea behind. So, basically the best way of dealing with this kind of things, for example, if I want to have this well separately, instead of having in the same platform, I have a well platform separately, I have a living platform separately, kept apart say few hundred meters. That is the best design, is not it, and keep the central processing platform separately. So, 3 jackets, 3 top sides, which will be the good design, but you will be spending 3 times your requirement for design and analysis 3 times. So, you can see here the cost of the facility goes as big as 2.5 to 3 times. So, that is why you try to combine, but at the same time you try to provide safety which is built into the system, that in case of a fire either in this well platform area or process area does not affect or to minimize the risk, is not it. Even if you go for 3 well platform, 3 platform with 1 living, 1 process, 1 well, you will not be able to conclude that there is 0 risk. You still will have a risk of some other means of fire. So, basically that is where kept minimizing the risk, at same time looking at the overall implementation cost. So, in here also you will see that the reason why they have kept the well at the middle is just for convenience. If you have the well at the center, the drilling becomes easier, whereas the keeping the well on the right side, you will see that there is potential problem of designing the jacket, because the drilling rig is quite heavy. You see here this particular project where the well platform is on the right side, kept separately, because this is a gas field, and potentially most of the time or 99% of the time gas well platform will not be combined with the process platform. If it is oil platform, there may be potential chances of combining this with this, but never if it is a gas platform, because of high potential of fire. So, you see here in this particular case, well is separated, process, utility and then the living logically organized, so that you have the least hydrocarbon coming onto the living facility area. So, you could see that this is one of the design, but if it is just not gas, if it is an oil platform, you will see that they are combined together, all of them, every one of them, all these 4. So, you will see the next facility is something similar, is actually a oil platform, and you see everything is stacked together in a bigger space, and basically have saved 1 jacket. That means cost economical, but you could not do this, because here it is a gas type of oil platform. So, basically we have no choice. You could also see in this particular case FPSO, well and process together, but well is kept exactly at the middle. You can see here the reason why we cannot do this drilling at the either on the stern side or bow side of the ship is very difficult. The stability becomes quite troublesome. In fact, the motions become very large. So, if you keep at the center, motions are very minimum. So, that is why we keep at the central, and you have probably utilities on one side and kind of living, and then the remaining of the process facility on the other side, just a arrangement there. Semi sub, you can see the drilling is exactly at the center, but surrounded by all the facilities, because that is what is possible by this type of floating structures. You won't be able to keep the drilling mast on one side and can have a very serious stability problem. So, you could see that the idea what you want to learn from these few pictures, there is no fixed rule. You can make your own arrangements as long as you follow and evaluate and minimize the risk of fire, safety to the human. So, that is the idea that you need to work out. So, what we need to look at basically design against fire, basically you need to find out whether what type of fire, whether it is a pool fire or a jet fire, that I think we will just quickly look at. Pool fire, basically after the fire, if there is a spillage on the floor of a particular location, large amount of fuel, then the fire will be almost like a spread fire, just over a larger area. So, you have the fuel spillage on the ground or on the floor somewhere, whereas the jet fire, fire is occurring, but then there is a high pressure fluid, hydrocarbon oozing out of a pipe, oozing out of a bigger tank or a process equipment. So, basically it will come like a high speed jet, and which can go for a longer distance, number one, and destroy several things which are secondary in nature, for example cables and facilities. Of course, may not be able to destroy structures unless the structure is so weak, but combined with the speed and the fire effect can even destroy smaller structures. So, that is the potential of the jet fire and the pool fire. Pool fire is just the flame formation for the larger area on the ground or on the floor. So, we need to see what type of fire occurs, because the effect is going to be slightly different. Location, for sure we need to know, size, basically the extent, and the intensity, basically the time duration. So, these are the effects which we will put on to steel structure and see what exactly is going to happen. Heat flow characteristics, basically the type of flame, properties of steel at elevated temperature, because using this information we can simply go and look at the steel. When you heat the steel, how the stress strain characteristics, basically that is what we are interested as a designer. We want to find out how the design stress strain curve changes, whether it goes higher or lower, whether the slope changes downwards or upwards, which is of very much importance for us, and which can be definitely simulated, or you can do a testing, heat the steel and then go and do a tensile testing. And then we will also look at alternate means of protecting the steel from obtaining this temperature. For example, there is a fire, as long as you can provide a barrier between the fire and the steel, then you can actually make the steel to feel only a particular temperature. The temperature outside can be 900, 1000 degrees, but if you have a barrier which can only just conduct say 400 degrees, not more than that, then it is, you only need to design the steel for 400, though the outside temperature is 1000 or 1200. So, basically this fire protection several means, that is why you see nowadays many of the buildings are built basically steel, because steel you can make the construction faster, but not very good in fire safety reasons. So, what normally is done now, you have the steel structure, but completely protected by concrete surfaces. So, encased steel structures you will see many places, like conventionally we go for RC structures which takes longer time for construction, you have to go sequence, whereas if you make the steel building and just cladding with the concrete or grouting, which is very fast compared to. So, this fire protection you should get into your mind, concrete is very good against for surely fire protection mechanism. Fire can be classified into cellulose fire and hydrocarbon fire. Basically, I think cellulose is the organic material, and that happens like fire in the forest, fire at your home. So, cellulose fire is not directly related to any of the hydrocarbon material, which has got certain characteristics. We can compare how the temperature rise and what kind of temperature rise it happens, which is what is our importance, how fast the temperature can reach say 900 degrees. You can compare a conventional stove with the gas stove, you can see the time taken to rise the temperature to 900 degrees, you could easily find it will take a longer time when you use the firewood. When you use the gas, you will be able to reach in few minutes. So, that makes the difference. So, the organic material, the fire rating is very low, and what we are interested is, because we definitely do not have this problem in the offshore platform, at least because we do not have any organic material in construction, whereas if you have houses or other facilities, you may have such type of fire. In any case, it is not a big botheration, because the temperature, the rise, the rate and the duration will be quite small. Hydrocarbon fire, as I mentioned earlier on, pool fire, jet fire is a typical classification depending on where the fire occurs, and the amount of fuel coming out basically is important. Combined pool and jet effect also can happen in cases where actually you have a eruption in a vessel which keeps on pumping out the oil, and you form a pool, and that continuous supply from that particular equipment keeps burning your the structure. So, many times you will have the pool fire combined with the jet fire, because in the vicinity, if you have a equipment, it will just erupt. Cloud fire and fireball, I will show you some of the photographs, probably I might have a video. You could see that, especially gas type of platform, the fireballs comes out, could be potentially so large, bigger than the platform size. Such eruption comes out, it is like a huge cloud and full of fire. Typical the temperature rise versus the time, you could see this graph. The bottom one is basically a cellulose fire, is the temperature reaches around 900 degrees at the time duration of an hour. You can see here, if you just go around here, almost about an hour to reach a temperature of 900 degrees. Whereas, if you look at a hydrocarbon fluid or the gas type of material, probably I think I can conclude the same 900 degrees can be reached in 7 minutes or 8 minutes. So, that is the type of difference we are talking about, is 1/5 to 1/6 quicker it reaches 900 degrees, because at 900 degrees no steel can withstand its integral strength, it will just fail by melting. So, basically that is the idea, that if you look at 600, 700 and 800 degrees, steel can't withstand unless you have a protection around the surface. So, if you are able to, if you have a normal fire, you do not really have to worry, because it takes almost 30-40 minutes to reach such a state. So, that by that time you can evacuate people and go away, whereas the hydrocarbon fire is so quick, within 10 minutes if you are unable to evacuate, your structure will become unstable. So, that means we need to provide by means of making the structure to reach temperature within the limits of stability. That is what we are going to define, what temperature is that, whether it is 200 degrees or 50 degrees, we can define a temperature and make sure that we have the barrier in place for all the structural components, that we can limit the temperature to say few hundred degrees. So, that I will be able to save human life. So, this graph is very important, but what we are going to have is only this graph based on, actually it is coming from Department of Energy. They have done one joint industry project, you see here DEN, Department of Energy UK guidance notes. This curve is based on actually the field testing, they have made a few fire testing, and also adopted by this curve is adopted by Norwegian Petroleum Directorate, basically it is their guidance notes. Of course, this is coming from one of the British code, is designed against fire resistance structures. So, what are the fire protections? Basically we have active, passive. I think active, I mentioned about water spray deluge system. I think every building nowadays is mandatory to have, especially industrial buildings should be having fire deluge system. So, you will see, if you have gone to some of the factories, you will see fire deluge valves and spray nozzles fitted onto the roof of the structure. So, in case of a fire you will have a fire and smoke detecting devices. You will see two of them in the roof if you carefully look at it. One of them is a detection device. Once fire or a smoke is detected, what will happen? First thing is the alarm will come and the alarm will trigger the motor system to start the pumping and open the valves. So, automatically the water spray system will on. So, basically this water spray deluge is nothing but a network of pipes connected to the facility to a fire hydrant where continuous supply of water can be there. So, you need source of water and fully pressurized all the time, that is the main important thing. You cannot start the pump and start pressurizing at the time when the fire is occurring, there is no time. So, that means all the time the pressure should be maintained on the pipe. The pipe is fully enclosed with valves everywhere, but valves are closed and the pressure should be maintained, means whenever the pressure is down the pump needs to switch on automatically, and whenever there is a fire the spray nozzle should open with the necessary pressure to distribute the water to a area designated. For example, if you have only one nozzle here, you need to have larger spray distance, that means more pressure is required. Basically water deluge or water spray system is inherent for industrial structures and offshore structures is definitely yes, but for residential buildings it is not made mandatory. So, what you may see actually will be a fire hydrant, but then the firefighting is done manually. Firefighters will come and connect to the hydrant and spray water. Foam systems basically is definitely a requirement for oil and gas terminals, especially on land. You will see a foam spray on top of the fire which can put the fire very quickly. So, it is a halon system, just basically do not spray water, for sure you know very well electrical fires. So, you will have a spray gas. So, halon system will be there, and then carbon dioxide you might see in many places in public buildings, you have the carbon dioxide cylinders, small ones handy. So, you should know how to operate. So, all of them is basically an active system to put the fire down at the starting point itself. So, you do not allow it to propagate. As long as the systems are automated, you can actually prevent from propagation or even from going into a higher temperature. Only thing is automation becomes a difficult process. Sometimes you do a manual, sometimes you do a automation system, but for offshore we use this, and both of them are fully automated. So, there is no situation that somebody have to go and open a valve, somebody have to go and open a or switch on a pump, which will become potentially not good. So, everything is fully automated. Passive systems basically to prevent. So, though we cannot actually prevent the fire, fire is occurring, and then we need to protect the structure with a particular type of material wherein it could absorb the electrical energy and conduction is reduced. That means, you need to see the material which is not conducting that fast, and basically the temperature on the steel surface is limited to a particular value. So, that is the barrier we are looking at. The simplest barrier is very easy to identify as a cementitious material, concrete skirt. So, you have 100 mm thick concrete on top of a steel surface. The concrete takes a larger effort or energy of the temperature prior to transmitting the temperature to the steel surface. So, that is exactly the idea. So, cementitious materials are very heavily used in onshore structures, especially if you go to industry, factory, refinery, you will find every structure is protected with cementitious coating, just 20 mm, 30 mm, they will just have a coating on top, which is no problem, because on onshore structures we are not worried about weight. You can keep on building whatever you want, isn't it? You just, because cementitious materials are very cheap, it is not very expensive, of course, comparatively not. So, basically barriers for steel structures, the simplest means is encasement with concrete, which I think very heavily practiced. But for unfortunately for offshore structures, we cannot keep on increasing the weight, because either it is a floating structure or the fixed structure. We have a problem in our hand. If it is a fixed structure, design becomes too heavy, transportation installation becomes too difficult. If it is a floating structure, payload increases, then it becomes a serious problem of design, because you need to make the floating system bigger and bigger. So, that is why we need to find alternative solutions wherein we can have a similar effect, but then lighter material or other forms of functions. For example, if you look at the subliming coatings, heat energy absorbed by transforming solid to vapor. So, basically you have a very thin layer of this coating material. When it is affected by temperature, it actually vaporizes. The vapor is the barrier forming between the temperature or the fire to the steel. So, you have a cloud of this material, but directly from solid to vapor. So, you will see a few hundred layer not permitting the flame to go through and go into the structural surface. So, that subliming coatings quite expensive, but the thickness of the coating may be 5 but at the time of temperature increases, it actually vaporize and form a thick cloud, which does not permit the direct contact of the fire with the steel. The intumescent coating will expand under fire, forming a foam like material, very similar, just like our foam. So, basically it gives a semi solid protection, basically between the fire and the steel it will form a kind of thick material, but not so thick, it is just a foam type of material. So, both of them, the original thickness will be very small, 5 to 10 maximum, density is lower than concrete. So, you have similar characteristics achieved by a smaller thickness, less weight, but slightly increased cost. So, that is where we look at, either we use subliming coatings, normally not used in many facilities, but this intumescent coating is well preferred, because this has been in use for several decades, and basically you go through net, you will find so many vendors of different chemical composition you can find. A typical fire, you can see here the longer the or the larger the radius or the distance away from the center, you will see that the the heat energy will be reducing. That means, if you try to go closer and closer, you will not be able to survive. So, we need to locate the safe facilities when a fire occurs on a particular location, where you should have the master switch, in case if you have to have a changeover from automatic control to. So, you need to locate them properly. Sometimes we do a specialized study, each fire location is assumed. So, you find out which will be the best position for the control valves to be located. You do not want the control valve to be located in a hydrocarbon area where the fire occurs, the control valve also get damaged. Basically, I think just to give you an idea of what this heat radiation means to personal survival, just to greatest solar radiation in terms of kilowatt per square meter is about less than 1, and working areas where personnel are continuously exposed slightly 1.6, where personnel may be continuously exposed in general areas about this much. And when you look at around 10, people working in sunlight in a hot area is about 1. When you talk about around 10 kilowatt per square meter, then probably you will not be able to sustain, you will not be able to stand. So, you need to just get away from there. So, that is the type of number we need to know, because when you go back to this picture, when we do a fire study, we need to find out the escape paths are not across such radiation levels in case of fire or in case of operating situations there. I think we have already discussed this, basically different applications to different type of structures, type of bulkheads. So, it may not be that important basically. Also, application of the passive fire protection to different classes of structures, valves, basic idea is what is preferred. Mostly you can see here spray applied coatings, which are intumescent type, and most of them mostly just apply like a spray paint. You might just see, normally we do painting of walls, only thing is it needs to be applied by experienced personnel, so that the thickness of the coating is uniform and then stick to the surface of the steel, otherwise it will just come peel off, is going to be a problem. Sometimes we have special sections like, for example, prefabricated sections with the seals. For example, you want to have a door, your barrier is all around the building, but if the door is not fireproof, what will happen? Fire will encase through the door. So, you need to make the door fireproof. So, in this type of cases we normally do not basically spray on the door, but you have a prefabricated material of that kind, you make the door out of that material, but then the sealing between the door and the fixed component needs to have fire protection, cannot use a fire material like rubber, you cannot use. So, you can see here when you want to make a particular structure fireproof is not so easy, because you need to make sure every component is well behaved during fire, especially something like this penetration is very important. For example, you have this building, for sure you will have incoming outgoing systems, for example, the electrical system, plumbing system, you have a plumbing pipe coming in, and if that pipe is not designed, fire can come through that, or you have that sleeve, the connection is not sealed, smoke can come. The main problem of or the cause of death during a fire is actually not directly fire, many times smoke causes tremendous effect, and basically that means you need to make sure the sealing should be 100% correct, that smoke does not enter into the facility. So, basically just an example to give you what are the things you need to look after during design, and this the best way of looking at the layout, which I think you have seen the photographs, basically the well area, process area and safe area or living area, purposefully I have put safe area. Basically the barriers is a wall, which is what normally we do in onshore or the building structures. You have a barrier which is nothing but, you can make it soundproof, fireproof, blast proof, isn't it? Most of the buildings we make the walls for soundproof basically, and then if you have potential of having fire, you make a firewall. So, instead of making a brick, you may actually go with concrete wall. Some cases of buildings, you know, you will see that some of the walls are made of concrete, just to make sure that they have sufficient fire resistance. Instead of normal conventional brick, you will use a concrete wall, and you can design the concrete wall with sufficient reinforcement, which can also take the explosion or blast resistance. So, basically that is the idea. So, these barriers are nothing but a structure capable of resisting high temperature and higher loading for rising from blast. So, basically we call it firewall, fire and blast wall or blast wall, sometimes you design for both. And basically whenever you have this safe area in the vicinity of the process area, you need to make sure that double safety for something like this. You see here, when you enter here, you have double door. So, the first door opens, the hydrocarbon entering into the room is avoided because you have another lock. So, this is called the airlock, is nothing but a double door which separates the entry of any foreign material like hydrocarbon gas, smoke, especially smoke entering into this particular. So, all the time one of them is closed, then there will be an exhaust from that particular chamber. So, that whatever is entering is recycled and surrounded by firewall all around the facility.